discussing Neurips Part 6. This is a discussion of 3 papers that are kind of similar. They're papers about reinforcement learning and how pre-training and transformers can influence, help, improve reinforcement learning. They're also trying to understand why pre-training works in certain cases and why it doesn't in others. It's, I think, an important bridge towards the concept of transformer architecture in robotics in general and reinforcement learning in particular. If you think about reinforcement learning is active decision-making on the fly with feedback. And that's different than other types of learnings. Let's say you have what's called off-policy learning, where things like imitation learning or self-play, in the case of Atari or Go, where you have you learn from interactions or from some sort of offline data set, and then you apply that to the actual. You don't learn while you're doing. You learn sort of in an offline, supervised way, and then you apply it to the action, and then you see what happens, and then you go back and you keep improving. So there are different approaches to reinforcement learning. I'm fascinated by this because I have a sense, my gut's telling me reinforcement learning is much more powerful than it's being portrayed currently in the machine learning community. And that's because reinforcement learning is, in essence, what humans are doing. And what, of course, computation can help is with the acceleration. In an essence, reinforcement learning is another word for iteration. Okay, iteration and error correction. So it's very Popperian in that way. And for people who have been listening to the Not Even Wrong podcast for a while, I hope you see that we're big fans of those types of concepts. So that's why we believe that reinforcement learning is a very powerful concept. Now, it's also in the sort of family of game theory and economics, which is part of my background. So that's why I'm fascinated by it. I also really like particularly Sergey Levin's work and his depth that he brings. He's not just I would say, average reinforcement learning researcher or AI researcher. He has some depth, some philosophy, and I like this. I like the theoretical approach. And these papers are exactly very good examples of that approach. This is Not Even Wrong podcast. It's January 11, 2024. This is Krim Delco. For the day, the fund is down 2.5%. The market's down 7 basis points. For the year, we are down 6.8%. The market's down 20 basis points. We're underperforming by 7%. Tesla is under pressure in several ways. I think the fundamental problem with Tesla right now is that we have some bad news coming from Hertz today, that they're cutting down on their electric car fleet in general. I think there's just a little bit of a scare of volume. I think that's the problem. But we've discussed this Hertz situation before. I think the fundamental problem with Hertz is that we're offering a Tesla to a customer base which is accustomed of paying, for very low-level cars. So this is a little bit like you're trying to sell a high-end boutique hotel to a customer base which is, accustomed to Motel 6 and is not willing to pay more. So there's a bit of that. Of course, it's not good news, and we believe that we're going to have to stick through these couple of weeks. Now, hopefully, the damage will not be as big, and we'll see what the volumes will do. There's also news that Tesla has to cut production in Germany for a while because of parts issues. So there's just bad news accumulation from everywhere, and we also had a warning from Mobileye, which we discussed yesterday. We actually believe is supporting the Tesla story. So this is in general why the stock is having a problem. Now let's talk about these papers. So these are 3 papers from Neurips. Let's start with pre-training for, let's just go, pre-training for robots. Offline RL enables learning new tasks in a handful of trials. The problem statement is, how can we devise methods that enable effective pre-training for robotic RL? Offline pre-training and fine-tuning. The goal in the paper is stated as, our goal is to learn general purpose initializations from a broad multitask offline data set and then fine-tune these initializations to specific downstream tasks. So what the authors are trying to do is take an offline data set of actions. And Sergey actually talks about this in one of his talks that I think Neurips 220, where he gives a speech about this. Imagine a power plant that has certain actions, like we're increasing the voltage when the weather is such, we're decreasing when the weather is such. Imagine a doctor that has certain prescriptions to certain patients in certain circumstances. You could learn that and then use that learning for a robot, and then keep doing, tell the robot, okay, now go out and write prescriptions, or go out and manage the power plant. So in a sense, what they're doing is, it's kind of like supervised learning, right? Offline reinforcement learning is supervised learning, but within an action space. And the key is, it's off-policy learning, so you're not adjusting your policy while you're acting, you're adjusting your policy in a learning process, and then you're using that policy in action, and then you might restate that. Within the context of this paper, I came across the PhD thesis of Aviral Kumar, who has written about this. Now, his thesis, it reminds me a bit of Yannick's thesis, because it's a theoretical approach towards reinforcement learning. And by the way, the parallel has nothing to do. Yannick's was about GANs and how they act, but the similarity is in terms of looking at the statistical properties of the particular model or algorithm and trying to understand when it works, when it doesn't work, trying to dissect what it is that makes these things work and how we can mitigate problems. So that's the similarity. Let's get back to Kumar's thesis, which is related to this paper. What Kumar talks about is, okay, how can we build a data set driven paradigm for RL that can incorporate static, previously collected data sets for making effective decisions? Okay. So a dataset-driven paradigm for RL bears the promise of translating progress in collecting datasets and advances in deep learning directly to generalizable and powerful decision-making engines. Okay, so what they're trying to do here is, Aviral's thesis under Sergey Levin is, okay, look, we have a history now over 10 years of supervised learning and data collection for, pictures and dogs and cats and stuff like that. Can we now apply this to what they call effective decision-making engines, okay? Decision-making engines. So this is now not about classification. This is about making decisions. When should I cut the power in the power plant? When is the fire hazard high? So I should maybe not pull voltage in the power plant, or the prescription example. So what they're trying to do is translate the culture of machine learning, which is data collection and supervised learning, and apply to decision-making agents in an RL setting. Now, what Aviral in this thesis notices is, of course, that there's a problem with that, which is called the you could have a situation where what they call a distributional shift happens. What that means is that when you learn offline RL, you are, in a sense, learning from a distribution of data, and then you're applying it to potentially a new type of situation that hasn't been learned. And that could lead the agent to completely go off track and basically do stupid things. And Aviral is trying to mitigate that with certain techniques and so on and so forth. I don't want to go into details about that. but it's being discussed in this particular paper. Now, to finalize against this conversation, so what this Neurips paper, pre-training models in offline settings, is talking about is, okay, we can actually train robots in an offline setting and then apply them and have translatable, generalizable skills applied. It's possible. They've done some research on this. They've used experiments. I don't want to go into further detail. I just find it interesting. This is, of course, incredibly important for, let's say, self-driving cars. Imagine you could have offline learning in a car, or you could use the Tesla data and the shadow mode data as an offline data set and then apply to the car. And that's probably roughly what Tesla is doing. So very, very important work here. Next paper is When Do Transformers Shine in RL, Decoupling Memory from Credit Assignment. This is a theoretical paper that looks at memory and credit assignment. In other words, it looks at, okay, what is it I need to remember to keep doing my task? And the credit assignment is of whatever I remember, which particular actions are key in terms of me making the right decision. So those are the two questions they ask, and I find this really fascinating. You know, when you study reinforcement learning, you really get it's so close to home, because this is how we humans learn, right? We have a memory, we remember things, and we try to learn from memory. And that's one thing. The other thing is, okay, let's say, what is it that I really need to know within that memory? Let's say I remember, how to surf or how to ski or how to solve a math problem. Fine, I have my memory of how I do that, but which particular action within that memory has actually led me towards making the right decision? So what this paper is trying to do is try to understand how whether reinforcement learning has any particular advantage when it comes to transformers. So when we have transformers and reinforcement, when we combine transformers and reinforcement learning, what we're doing here is really looking at the transformer architecture, self-attention, and then apply reinforcement learning to that. So here now we're trying to understand, okay, what is it that a particular agent remembers, and how far back does it have to remember to still be good, and is it better than other models? So this is the key. What they find is that when time steps are long, transformers do better than other models, in particular LSTM, long short-term memory. Even in shorter time steps, transformers do better. So in a nutshell, transformers are good at remembering stuff. And that kind of makes sense if you think about it, because what is a transformer? It's a condensed knowledge base. So we have a lot more knowledge here than in, let's say, recurrent networks, where knowledge gets kicked out all the time. So we have to acknowledge that the compute power and the compute budget and the power budget of transformers is immense, particularly when we go multimodal. But the advantage is we have a lot more memory to work with. Memory not in sort of flash memory type way, but in a way like this thing knows more, so it can draw from more knowledge. When it comes to credit assignment length, which is the question, okay, which action is it that makes me do the right thing going forward, right? In that sense, it looks like, at least according to this paper, excuse me, transformers aren't particularly good. So they don't offer a lot of advantage here. So this paper states that transformers are good at memorizing, but not so good at knowing why they know things. To me, this is the tautology. You train a model on a variety of data and it becomes better. This reminds me of the local knowledge paper that I discussed previously, where they state that knowledge is local in the sense that data is learned sort of locally. Think of the football field and the football player learned within the context of a big stadium. That's localized, and this data is well understood, but then you wanna transfer that to playing football on the beach. You need in-context learning. So transformers are not very good at understanding these relationships, but with prompts, we can actually improve them. And I think this is really where, to me, where the rubber meets the road in AI, real AI, general artificial intelligence. To me, the road towards general artificial intelligence is really paved on being able to apply things like in contexts, being able to, so you have this large amount of memory, and now you need to learn how to apply prompts, self prompts, like Eureka, remember, reward functions, like evolve your own technology, your own algorithms to take advantage of that knowledge. This is, to me, where the rubber will meet the road. But this paper states that in general, good for memory, not so good in credit assignment. That's why we need in-context learning, which is my interpretation. Lastly, a paper bridging RL theory and practice with the effective horizon. In this paper, the authors ask specifically why pre-training and reward shaping in reinforcement learning sometimes work and sometimes doesn't. Reward shaping is when you help a robot learn in a sparse reward setting, such as a game of maze, where finding the goal is 1 and otherwise 0, but then you give it a little bit of rewards. Let's say you give it small rewards just for trying, and then you give it a little bit of rewards if it gets a few things right. So you try to nudge it towards the right solution. Now, ideally, if you think about it from a research perspective, a theory of reinforcement learning should provably show why deep reinforcement learning succeeds while using random exploration. It should also be able to predict which environments are harder to or easier to solve empirically. Finally, it should be able to explain when and why tools like reward shaping or initializing with a pre-trained policy help make RL perform better. So what this paper finds is that it introduces the concept of the effective horizon. And the way I understand the effective horizon is that, think about it this way: you randomly try to explore policies until you find something that gives you a good reward, and then you stick with that. And you stick with that until it doesn't work, and then you do random again, and then you stick with it again. And the question is, how far is that? And what they find is that when you have a sparse environment, it's really difficult to have good solutions with reinforcement learning. Sparse means when you have just a reward of 1 if you hit the goal, and otherwise always 0. But when you have more information within the context of your task, you can have, let's say if you have a shorter effective horizon, you do much better. So in problems that are less sparse, or where we have more information about how to get from A to B, maybe we have, A1, A2, A3, where we have maybe, like in investing, you have certain, like every earnings call, you have real valuable information that gives you a sense that you're on the right path towards wealth creation. That's when you succeed. And when it's sort of waiting for Godot, and then once in a while you hit the jackpot, sort of like investing in a bad company, and then once in a while they get taken out, like Juniper recently. That's a frustrating business where, there's not a lot of intelligence actually to be used. So intelligence in this concept, or learning, means that what we're actually learning is we're learning a reward function that is able to navigate a otherwise sparse environment. And the reason the reinforcement learning, or what this paper is asking, is really, why does reward shaping, for example, why does reward shaping sometimes work and sometimes it doesn't? Well, it works when the shaping has some signal, right? So when you're in a situation where the reward shaping actually is signal towards a goal, well, then it works. So again, it's maybe obvious, but of course, what these people are doing is they're setting up a concept, a research concept. They're testing it. So this is more than just anecdotal knowledge. But if we just sort of summarize this paper, we can say that, look, in general, a reinforcement agent is randomly exploring until it finds something with a reward. then it sticks with greedy, meaning it keeps doing that. It sticks to its policy. It keeps doing the same thing until it gets a bad reward, and then it does random again. So, and that effective horizon, which is from sticking towards unsticking with the policy, that the shorter that is, the harder it is. Or in other words, the longer, the more information I have with the greedy action, the more the greedy action helps me get to the goal, the more success I will have. And if that horizon is short, then I need to find ways, maybe with reward shaping, to solve the problem of a short effective horizon. This is the way I understand it. Again, it's subtle and it's deep, and it's not gonna, solve for self-driving tomorrow, but it's gonna give some step-by-step intuition of how to design algorithms, and more importantly, how to collect data and build hardware to exploit the particular domain that we're looking at. So to summarize, 3 papers in Neurips. This is part 6. The 3 papers that I'm discussing here: paper number 1, pre-training for robots, offline reinforcement learning, and how that can help us generalize for tasks that haven't even been learned in the offline context. Using offline reinforcement learning also helps leverage the whole infrastructure of data collection that already exists in AI. Second paper, when do transformers shine in reinforcement learning, decoupling memory from credit assignment. We understand here that memory is a good thing and comes with the transformer. Credit assignment not so much, and that is something transformers are not particularly good at. And third, bridging reinforcement learning theory and practice with the effective horizon, which is basically saying, okay, look, in general, RL works really well when we can randomly explore until we get to something with a good reward. Then we stick with that until we get to a less reward, and then we do random again. This is kind of another way to say we do iteration and error correction, and we have to find a way to iterate at a low cost with low error correction. This is more sense. Thank you.